In this video, we work problem 108 from the Larson Calculus text, 10th edition. Here's the problem statement. It says a car is driven 15,000 miles per year and gets X miles per gallon. Assume the average fuel cost is $3.48 per gallon. Find the annual cost of fuel C as a function of X and use the function to complete the table. So we're given a table like this with rows, and we're given X values 10 through 40 and increments of 5. We're asked to find C of X and dx. The first thing that I write down always when I'm reading a word problem like this, is what my variables represent. So they say find the annual fuel cost C. So I'm writing C of X. So and then I just tell myself, what does C of X mean? Well, it's the annual fuel cost in number of dollars per year as a function of gas mileage, which is some number of miles per gallon. And so I specify that that's what X represents. I remind myself what the units are. And then I say, okay, what do I have? What do I know? Well, my problem statement says that the average fuel cost is $3.48 per gallon. So I write $3.48 per gallon down. And I also know that my car, that I have a tendency to drive 15,000 miles per year. I personally don't have a tendency to drive that much, but usually I think 10,000 miles per year is good for most people. But this person in the problem statement drives about 15,000 miles per year. So then I write that down. I just multiply those two together. And then I look at the units. I say, okay, I've got 3.48. Those are dollars, and I've got years in the denominator. And that's what I want for my annual fuel cost. I want some number of dollars per year. But I've got this number of miles in the numerator and this gallons in the denominator. And I want to bring X in somehow. Remember, X is the number of miles per gallon our car gets on average. So we'll say, okay, I've got miles here. I want to get rid of the miles. I've got gallons here. I want to get rid of the gallons. So I'll put the X in the denominator because I know I get X miles for every gallon. If I put X miles in the denominator and 1 gallon in the numerator, the miles reduce, the gallons reduce, and we get some number of dollars per year. If we multiply straight across, we get this 52,200 number. And then if we multiply straight across here, we just get an X in the denominator. So this is our annual cost of fuel in dollars per year. So now I'm going to go to desmos.com, and we will create a table of values and then populate that table with both function values for C and then the derivative of C as well. So I just typed in C of X equals that number divided by X. And I know that I want my X to be positive. So I type that in. I get this curve, just like Y equals 1 over X. And we're just talking about that branch where X is greater than 0. And to create a table of values, all I did was hit return there and then plus the little touch this little plus sign, put a table. And then I'll start with 10. And then 15, and then it automatically populates with 20. I want to go all the way up to 40. And then for my second column, I want that cost at each of these X values. I've already typed my cost function. And I'm using X1 rather than X so that I can save the X for my variables in the definitions of the functions themselves. And so at these X values, these are the function values. That's the annual cost for different amounts of gas mileage in number of miles per year. So those are those points right there. And then we're asked also to compute C prime. Now, if we just type C prime of X1, it automatically populates that table. We can find C prime ourselves by hand by doing just a little bit of algebra. And so we will rewrite this expression first, and then we'll use the power rule to get this expression. I'll do that on paper. So C prime is dc dx. So it's the derivative with respect to X of this expression. Now this you can think of as a product of two fractions. It's just this number divided by 1. times 1 divided by x. And you can tell that that actually works because if I multiply straight across, I get this number divided by x, which is what the original function was here. So I've just got a constant times my 1 over x, which makes it easier to take the derivative than, say, using the quotient rule. You could use the quotient rule here, but anytime I have a constant in the numerator and denominator, I always want to rewrite first. And so we can use a simpler rule than the quotient rule. So we've got this number, just write it down. And then we're going to take this 1 over x and rewrite it as just x to some power, x to some particular exponent. And we do that using this rule. If I've got 1 divided by x to some power, that's the same as x to the same power, but negative. So we bring that up to the numerator, bring the x up to the numerator, and that's fine as long as we change the sign on the exponent. So this 1 divided by x to the first is an x to the negative 1. When we take the derivative of a constant times x to some power, we bring the power down. We multiply this constant by the power, and then we multiply by x to the 1 less power. Negative 1 minus 1 is negative 2. This times this is that negative in the numerator, and this x to the negative 2 can be rewritten as 1 over x squared. And then again, if we multiply straight across, we get this negative 52, or negative 52,200 divided by x squared. Now, this is the instantaneous rate of change of this particular function. And if I want to sort of think about what that means, this is the instantaneous rate of change of this variable. That's annual fuel cost in number of dollars per year with respect to x. That's our fuel efficiency, our gas mileage, and some number of miles per gallon. So if I plug in a particular number of miles per gallon, let's say your car gets 35 miles per gallon. Well, then this is going to give me the rate of change of fuel costs, the instantaneous rate of change of fuel costs as we go from 35 miles per gallon to 36 miles per gallon. So our car is getting even more fuel efficient and our cost is decreasing. We can tell it's decreasing because this function is always going to be negative as our cars get more efficient. So that's great. But we want to know how much we're saving every year, and this number or this derivative is going to tell us how much we save per year as our fuel efficiency goes up by 1 mile per gallon at some particular number of miles per gallon. So we know that that's true. Let's go back to the graph on desmos.com. So here's our C prime. I just typed that in. But just to confirm that that is the same function that Desmos is calculating when it calculates C prime, I'm just going to type C subprime of, let's choose 30 miles per hour, or not miles per hour, miles per gallon. We get negative 58. So remember what that means. That means if our car gets 30 miles per every gallon of gas, then we save $58 per year if our car goes from 30 miles per gallon to 31 miles per gallon in fuel efficiency. So if our cars get more efficient in using fuel, we're saving a little bit of money here. $58 per year. It's not much when you're at 30 miles per gallon. But if you only got 10 miles per gallon, you'd save $522 per year, which is pretty cool. Then we could do that for another value of x as well. We save $42 per year if our car goes from 35 miles per gallon to 36 miles per gallon. So if we want to, we can graph this function C prime. Passes through those points. And the last question says, who would benefit more from a 1 mile per gallon increase in fuel efficiency, the driver of a car that gets 15 miles per gallon or the driver of a car that gets 35 miles per gallon? And I think it's obvious that the person who benefits more is the one that's getting the worst fuel efficiency to begin with. The person that only gets 10 miles per gallon saves $500 a year, whereas the person that's going from 40 to 41 miles per gallon was only save $32 per year.